Back. Let's see here, where is my pens? My pens. So you saw the buck converter with the diode. And you know what is a boost? Boost is if you, instead of putting a voltage source here, if I put a capacitor here, and then I switch and put a voltage source here, and a load put on the other side, then you get a boost. So you get a boost with the capacitor on the input, this, and diode, and capacitor. And of course, that's why this one is V over VG is D, and this one is in opposite direction is 1 over D. Tap it on. V over VG here is 1 over 1 minus dy, because we really like to refer duty ratio with respect to the active switch. So there was D to 1 minus D change, that's all. Now how do we get from here to the buck boost? Well, if you look at these 3-port networks here, and you have a source here and you have a load here, but it's really ground and 2 ports. And you have this kind of a switch and this here. So here inductor was put on the output. Here inductor was put, node is put on the input. So what happens if we put this inductor on the ground? Then you get exactly, I don't know what's delaying this here. Now you have a voltage source and you have a capacitor. And you do the same what you heard from K, volt second balance on this will give that voltage gain is, I don't know, what is it? Maybe shut it down, open a new one, and see? Just change it to next one, it works okay. All right, so now this is your boost, buck boost, which has a current is going here charging, and then you have a capacitance. This current of course has to go this way, discharging, and therefore the polarity will be inverting to start with, and this diode will be this way. So this is now you get a converter, which is a third possibility, which is basically, if you look at volt second balance, then you're going to see that voltage is like this, and either it's a plus VG during the on time D, and during off time it is a minus V. Come on. Minus V. So therefore you have a VG times, why doesn't stick for it? Ink tools, pens. Color thickness, okay. VG, VG times D has to be equal V times 1 minus D, right? So therefore gain function is D over 1 minus D. So V over VG is D over 1 minus D. Now, this is what I faced when I was looking at these converters, and I was kind of puzzled. How did this come out to be this way? And then I concluded that, well, we can get a buck boost converter, the same D1 minus D function, if I start with a converter which, let's put a first buck, right? And then use this as a source for what? For the boost converter. L1, L2, here is a boost converter, and here's the transistor, again. This is D, and this is D, and what you're going to get? The same as a flyback or buck boost, except now this is polarity non-inverting, right? Okay? So now the question is, does it have to be this complicated? Really, it doesn't. Because what we can do as a first step, and I'll use now my famous way to erase, we can erase this capacitor. It doesn't do anything, right? Because DC current comes in and DC current comes out, and this capacitor only carries a ripple. So, you know, it's not essential. So, and then what we can do is combine these two into one, and what happens? Then we have what is known as a non-inverting boost buck, right? So, okay, logic. Clear mathematical logic and thinking. Not much to do with electrical engineering, in fact. And that's how I came up with the Chu converter. Because what I did then is say, look, if this is the case, how do you compare this with a flyback or buck boost? Because flyback is reserved for isolated version. How do you compare that with the buck boost? Well, you have here one transistor, and you have one diode like this. And tell me what is the difference between these two converters. What is the difference between this and this? Sorry, this one is minus, this one is plus. This is polarity inverting. But what strikes you first when you look at it? Come on, quick. What's the difference? Other than polarity inverting, positive polarity for positive input, negative polarity for positive input. What is the rest of the difference? One inductor, one inductor. What about switches? This one has 4 switches, and this one has only 2. Here comes the idea. Can we trade polarity inversion to reduce number of switches from 4 to 2? And flyback confers, that's true, right? So, and then, but what flyback does with respect to these two converters, it does one bad thing, and that is the input current in this one, if I recreate this, and let me just get the green, for some reason didn't take my green, the input current is a pulsing, and the output current is also coming in a pulse. That's no good, because only capacitor is filtering it out, but you don't have inductors to help out. And likewise on input, no inductor to help out. But the question is, do we have to put it this way? What about if we reverse the order and put a boost first and then buck following that? Lamp, right? Okay, so let's go to that and let's see. Okay, here. The OR, you know. You see, I have a magic eraser, which I hated to work with when I was in, oh, not this one, come on, this one should come, yeah, small, medium eraser, okay? Okay. Beats a chalk on a blackboard, right? So let's just do that, but before that I want to basically copy a couple of these blank ones. This is blank, so I copied it, paste, copy, paste, give myself more slides. Okay, let's do just what we said. Let's put now the boost converter first. And then output of this we feed into the buck. So it is the same as the other one. Buck in series with a boost, non-inverting buck boost, but this is non-inverting boost buck. Boost is first and buck, well, what is the difference? This one already has a non-pulsating continuous current because it's dictated by inductor, is continuous output current. So right at the spot, it's better than the previous one, right? But what about here? Now comes the idea, what we had before with the buck-boost converter, flyback, right? There is only inductor, but what we traded, we had polarity inversion of that, we traded to reduce number of switches. Now I'm saying, hey, this is non-inverting. Can I make it polarity inverting and reduce number of switches, right? And what happens is, you see this capacitor here is charged and then discharged, okay? And then of course you have this other interval charge and then storing energy in inductor and then releasing and storing energy in inductor and then releasing. What about if we make this capacitor not grounded? Remember? Just a duality. In the previous case there was a floating inductance and we grounded it and became a flyback, right? Now I'm just doing opposite. I have a grounded capacitor and I say, oh, let's make it floating. See what happens. And if I make it floating, and then this is a ground, then this is a source, and this is a load, and of course there is a inductance in the input, and this inductance in the output stays there. And here comes the magic. You know, I put here maybe my favorite blue color, if I can get, now here, all right. So now we say, oh, if this is floating capacitor, I can actually connect it this way and charge it. So this is my charging, right? And then this capacitor, if this is the diode, that will automatically, positive input voltage will forward bias the diodes and connect it this way. And guess what? I put a transistor here. This guy was charged plus minus, and when you connect a plus to the ground, this negative voltage reverse bias the diode, turn it off, and what will do? Discharge this way. Voila. 4 switches are now just 2 switches. Even better. This switch is bad from a circuit point of view and practical drive, because it's a floating. Even though converter is non-isolated, you have to have isolated or some kind of a floating drive. This main active switch is, you know, grounded. Even better, this diode, when it's replaced eventually, you'll probably get later to it, when it's replaced with a MOSFET will be like this. Actually not. In isolated version, this MOSFET will be opposite direction this way, but in the isolated version, you flip the dot connection, you get positive. This is negative actually in output. This is just like a flyback. Positive and this negative charges voltage, this is plus minus, and charges is plus minus, so it's polarity inverting. But so that is one big advantage, is that now there are only 2 switches and grounded. And guess what? I wrote my paper that way, and I was going to present in a conference, and I had to apply for a patent within 1 year after I presented the paper, and I scrambled that. But when I showed it my patent attorney, he says, "Are you crazy? You'll never get a patent for this." And I says, "What do you mean?" Because I did exactly describe it as I said here. Because a patent law is, if you can use logical steps to derive it, it is not invention. Invention is supposed to be something like you just, in the middle of a night, you woke up and you dream it, you don't know why it came out this way, you can't explain it, and so on. Now, do I agree with that? Absolutely not. Okay, but that's what it is. So you have to just tell them, this is what I get, this is what the prior art doesn't do, and what this does, but don't tell them how you got to it. And for me, that was the most important part of my invention of this converter, because in all inventions, and I follow the Nikola Tesla in that way, he was always saying, it is not the ultimate result, it is a logic how you went to it, which will lead you next time to come up with the better things, okay? And the same thing, you always look for a generality. You know, I'll give you one other thing, which this was all happening in that year. I looked at these two, and you know, one way to look at the converters is, let me look at this. One way to look at the converters is, I looked at the voltages, waveforms here, because it has only 2 intervals. You know, this one, it has only 2 intervals. It has this, positive and negative, volt seconds on this. And guess what? When I built the first converter with this, and I looked at the voltage waveform of 2 inductances, and they're identical. And I said, wait a minute. The identical looks like a transformer with a 1-to-1 turns ratio. Why don't I put it together? Okay? And I was so excited and ended up, went for lunch for a break and ended up in Professor Milberg, his wife, in one of his Chinese restaurants in Pasadena. And I said, Professor Milberg, I told him about this converter, and he said, okay, check it out. And I told him, hey, it works. And the next thing I told him, he said, you know what? I just think I want to couple these two inductors and put it like a transformer. And he's a man which has a lot of history in the circuit and so on, but first reaction is, you can't do that. This is not a transformer. These are inductors. That's why I eventually called it a couple inductors. And you know why you can couple it? Very simple. And I'll explain you two things, why it is couple inductor and why it cannot be a transformer and why it's a different structure. It looks like and smells like a transformer, but it acts like an energy storage inductor. And why? I didn't even, later, you see here, you can analyze it and find out the voltage waveforms are identical. But here there is a circuit tricks you can use, and let me do one of those. And what is a circuit trick? I look at this circuit, and let me do different color, which you can see differently. Maybe green. Okay, look at this circuit. Think about circuit components. Capacitors are short for AC, right? Short, correct? 1 of j omega c, and omega is large, so it is short circuit. So let's agree that this is short, right? What about the output capacitor? Let's agree that that's short, right? And what about the voltage source on the input? Let's agree that that's short for AC, right? I mean, we eliminate DC sources and these are DC sources. What do you get? What do you think? This here is one inductor, and if I put the dot here and put the dot here, this inductor is connected to here, right? And down to, sorry, I should erase it. So we have, so you have this inductor, capacitance is shorted, right? And this is shorted. And then this inductor, the other dot connection is also over here, and it's shorted to ground through this other part. So what do you have? You have two inductors in parallel. So what does it say? Whatever voltage is on one, it's the same voltage on the other one. Whatever Uri cycle you use, you can use a 10% or 50% or 100%, which is beautiful. You change operating condition, they're always there, tracking each other in a voltage, which means there is no reason why you can couple them together, right? Now, why they're not a transformer? Because in this one, God, what is this? Current goes in here, and the current goes in here. So what's happened? Ampere turns of both windings add together, and therefore you result in a device which store energy of one inductor, energy of the other one, so therefore it doubles energy storage. So if you make it, you have to make it with twice the air gap, etc. Now I come to another thing. What about inductor? What about transformer? The beauty of a transformer. But I have a question that I always ask, and don't feel bad. I fail 90% of electrical engineers because they don't know who invented transformer. So